Okay, so we're starting with power functions. We are not doing two sets of notes because we missed yesterday. We were going to do two sets of notes yesterday anyway. These are going to be short, pretty easy to understand, but definitely important for the next thing we're moving on to. So the first thing we're going to start talking about is power functions. And a power function is any function that looks like this. F of x is equal to a times x to the n power. A cannot equal 0. And n cannot equal 0, right? And it's a monomial. It's just one single term. There's nothing plus or minus after that, nothing at all. It's just one term. Okay, so a power function is also a type of monomial function. So we're going to draw a sketch of each, which will look a lot like our, well, they will look exactly like our parent functions because the parent functions all have one term as well. So for a constant, it's f of x equals c, and c is just any real number, right? So if I was to graph that, what would it look like? Horizontal line. Thank you for not saying a straight line because all lines are straight. So it is horizontal, and y could be anything. I have it down at a negative number, but it could be any number there. Then linear, of course we know linear is f of x equals x. So that's what this would look like. Quadratic. That's definitely old business as well. F of x equals x squared. That is your parabola. Cubic, we know, is f of x equals x cubed. And we know that it looks like this. Then we have quartic. Quartic would be f of x equals what, do you think? X to the fourth, exactly. And can anybody tell me what it would look like? Kind of like a parabola, exactly. It's going to look like this. And f of x equals x to the fifth is quintic. What's that going to look like? Kind of look like a cubic, yes. Okay, now they're not exactly the same, obviously, because they'd have different points. Okay, but if you think about what's happening, when you have an even exponent, all of your outputs there are going to be positive. So all of your y's have to be positive. When your exponent is an odd number, you could have negative outputs. Now, if I took this right here, right at this point of inflection, and I broke it, and I reflected this part back up over the x-axis, then it would look like this. Or if I took this and I bent it down over the x-axis, then it's going to look like this. So they're all basically the same thing. They just sometimes we can have negatives and sometimes we don't. So even though, again, this isn't going to look the same because obviously 0, 0, and 1, 1 are going to look the same for any of these that are related. But when I get to 2 here, this is going to be 2, 4, right? And this would be 2, what? 16, right? So it's going to be skinnier, but it's going to have the same shape. Does that make sense to you? So you need to know that when you have even exponents, they're all going to look like they're going to have the parabola characteristics. And then when it's odd, it's all going to have like the cubic characteristics. So if you can picture those two, then you know the shape, and that's a very important thing for us to know, okay? We're going to start sketching some of these things tomorrow. So it says if the function has an even power, then it is symmetric about what? The y-axis. Good. Makes it an even function. If the function has an odd power, then it is symmetric about the what? Good, about the origin. Okay. So that's a little review of even and odd, right? That symmetry is always important to us. Now we are still talking about end behavior. Tomorrow we're going to start looking at middle behavior finally, but still talking end behavior. Now these examples use quadratic and a cubic, but really it applies to any even power. So whether this was a 2, 4, 6, 8, 587,982, it doesn't matter. And then this is an even power, but with a negative coefficient. So if I have an even power, positive coefficient, and we're talking about these power functions, then it's going to look like this. And since there's no markings on here, and I don't know what the scale is, it's going to look like that. So my end behavior is always going to be as x approaches infinity, f of x would be approaching what? Infinity. And as x approaches negative infinity, f of x approaches infinity again. So that's in behavior is a true statement for anything, any of these monomials that have an even power and a positive coefficient. So when I have an even power and a negative coefficient, the only thing that changes is that it gets reflected across the x-axis. So even power and negative coefficient, as x approaches infinity, f of x approaches what? Negative infinity. And as x approaches negative infinity, f of x approaches negative infinity. And I know this stuff seems very redundant, like we've done it a lot, and it's the same kind of thing over and over again. But when we're getting to this point where we're going to start sketching polynomials tomorrow, you can't be hung up on end behavior. You got to understand that 100% in order to move on to the next part. All right, so then if I have an odd power positive coefficient, then it's going to have the cubic characteristics. So as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x approaches what? Negative infinity. So then odd power negative coefficient just has that reflection in the x-axis. So as x approaches infinity, f of x approaches negative infinity. And as x approaches negative infinity, f of x approaches infinity. All right, any questions about that? It's a lot of writing the same thing over and over again, but we understand what all that stuff means, yes? Okay, awesome. Then let's flip this over. So we're not doing all three of these, but we're going to do a couple just to get the point across here. Once it decides to turn, there we go. So it says graph each function and identify the key characteristics. So this is an x to the sixth, which means it has the quadratic characteristics like that, right? And so when I go to graph it, the only thing that's happening is it's being multiplied by 3, and that 3 does what? Stretch it. It's a vertical stretch, right? So when I start with my anchor points, 0, 0, well, the stretch does nothing, so I'm still at 0, 0. For the parent function, which would be f of x equals x to the sixth, when I substitute in 1, I get 1. So 1, 1 is another anchor point. So at 1, 1, that 3 affects my y value, so my new y value is 3, and then I can use symmetry to get the other one over here. Now for a quadratic, my next point is 2, 4, right? For x to the sixth, would it be 2, 4? No. What's 2 to the sixth? 64, because it's 2, 4, 8, 16, 32, 64, right? So it would be 264, which is way up there. And then I have to take that 64 and multiply it by 3, so it's like really way up there. So it's important to think about it, even though clearly we cannot graph that point, because this isn't coming from out here to be like wide. It's going to be really, really skinny and look something like this. But a whole lot better than mine always look. Let me do that again. There we go. And they have arrows on them. Okay. So my domain here is negative infinity to what? Positive infinity. Good. What's my range? Good. 0 to infinity. Do I include 0? Yes. What's my x-intercept? 0, 0. Do I include 0? Does that question even make sense? No. Then don't do weird things on your ordered pairs, okay? Because it's not intervals. I'm seeing some weird stuff on ordered pairs, and those are not intervals. All right, so it's kind of a trick question. All right, your y-intercept is also 0, 0. Increasing where? Good. 0 to infinity. Decreasing negative infinity to 0. Good. All right, so symmetry. We have symmetry about the what? Good. Y-axis. Do we have any discontinuities? No. Then our end behavior. As x approaches infinity, f of x approaches infinity, as x approaches negative infinity, f of x approaches infinity. Okay. Everybody okay with all that so far? Okay. Now let's look at this next one. So I have an x to the fifth. So parent function-wise, it has cubic characteristics, right? The negative is going to reflect it in the x-axis. The 2 is your vertical stretch. So I'm going to start at 0, 0. The reflection in the stretch does nothing, so it's 0, 0. X to the fifth being the parent function, when I substitute in 1, I get 1. So I can get both of those points in there pretty easily. But then when I substitute in 2, I'm not going to 2, 8 like I did on the cubic, right? It would be 2 what? 32, yes. So I'd go to 2, 32, then I'd reflect it, then I'd multiply by 2. It's like way off the graph, right? But again, that's important for you to think about because it's not going to come in real wide and do things. That's why some of you are having trouble kind of making this little wiggle in their work. It's real skinny because it's going to be way up there, so it comes down like this. What did I do? Oh, shoots. Yes, I didn't reflect it. Thank you. I didn't even multiply it. I just went to 1, 1 and made a point. I did nothing. Thank you. I was like, I did it wrong. No, I just didn't do it. That was my problem. All right, so let's start that over. Thank you for stopping me. So I'm going to go to 1, 1. Then I reflect it, if I actually do it, and then I stretch it by 2. So I end up there, and then this is the other point. Thank you. Then I would go to use the other ones, and it's really skinny, so it actually looks like this. There we go. All right, so our domain, negative infinity to infinity, right? Range, negative infinity to infinity. What's your x-intercept? 0, 0. Y-intercept? 0, 0. Increasing? None. Decreasing? Good. Negative infinity to infinity. Symmetry about the what? Origin. Discontinuities? None. In behavior, as x approaches infinity, y'all can write this out without me saying it. Okay. So it approaches negative infinity and infinity. Do we agree with that? Any questions at all? Awesome. Grab the other one. This is going on page 34. So we're going to talk about polynomials because tomorrow we're going to start sketching them. So this is the definition of a polynomial basically, and it looks insane, but it has to look that way because to generalize it, your coefficients are a sub n minus 1, a sub n minus 2. Basically, those are all of your coefficients are real numbers, okay? And a sub n cannot equal 0. And n is a positive integer, right? Which means that you are not going to have fractional exponents and you're not going to have negative exponents. Okay, so no negative exponents. It wouldn't be a polynomial if you did. Okay. So the last thing we just looked at, monomials, just one. What's your question? No, ask me a question. There's a lot of numbers. Okay. There is, but that just means like this could be 5x to the 7th plus 2x to the 6th plus 3x to the 5th, and it goes down, down, down. Okay, that's all that means. It just looks horrific, but it's the same type of polynomials you've done. All right, so let's talk about the shape and continuity of these. All right, so polynomials are smooth curves. Okay. And it's said that way because it doesn't come to a point at any time. So you know how in the absolute value it comes to a point? There's no pointy anything in a polynomial. Everything's smooth. So polynomials are smooth curves with no breaks. That means that there's no discontinuity. So it's breaks. So they are continuous 4, all real numbers. Okay, so your domain for a polynomial is going to be negative infinity to infinity every time. Okay, and they're continuous. Then we have the degree of the polynomial. Okay, so the highest exponent, and it's the highest, not necessarily the first, but the highest exponent n is the degree. Okay, so if your highest exponent is a 4, then it's a 4th degree polynomial. And polynomials are classified by degree. And some of them have a special classification name that's not just a 4th degree or a 5th degree or whatever. We'll talk about some of them. Actually, they all do, but when they get bigger than 5, we don't really necessarily talk about them that way. All right, so let's look at these examples of these functions here. We're going to start from the bottom here. So this one, highest degree is 5, so this is a 5th degree polynomial, or a polynomial of degree 5. Then 4th. Now you got to be careful not always just to look at the very first one. If they're in order, then it's the first one. But if they're not, they're mixed up, it's the highest one. So this degree is 4. This one is obviously 3. This one's 2, 1. And then this one's 0. Doesn't have any variables in it at all. So when you classify them, again, it can be a 0 degree polynomial, a 1st degree polynomial. But this one here is going to be a constant. They have the same names as what we just did with the monomials. With this 1st degree, this is linear. 2nd is quadratic. 3rd is cubic. Oh, that is not. I was going to use a Q there for a second. Cubic. And then what do we call the 4th? Quartic. And then 5th? Quintic. Okay, so then the rest of them kind of follow the same pattern as polygon names. So if we're going to follow along with polygon names, 6th would be what? What's a 6-sided polygon? A hexagon. So it would be a hexic, and then so forth and so on. Okay. All right, but it's okay to call it a 6th degree polynomial. That's fine too. Pentic, yeah, but it's quintic. It's sometimes there's different words that will mean have the same meaning as a different prefix. Yeah, quintic sounds better, right? But they're not the same. But the rest of them follow along. Okay, so the power and coefficient of the leading term determines the end behavior. So when we start sketching these now I'm talking about polygons. When we start sketching the polynomials, then we're not going to have a graph. We're going to have a function, and then we have to know how to graph it. So we have to look at the power and coefficient. So if I have an even power positive coefficient, right? And this little chart looks exactly like what's on the bottom of the first page of notes we had, right? So we're not going to copy down everything we did. We're going to write it differently here because we already wrote out as x approaches infinity. What we are concerned with is end behavior before we start talking about middle behavior. So if I have these are monomials that would look like this. But if I have a polynomial and it's a 2nd degree, it's still going to have the same end behavior. If I have any even power positive coefficient, the end behavior is going to be up, up. We don't know what's going on in the middle yet, but it's going to look like that. Okay, so if I had, 3x to the 4th plus 2x squared, so forth and so on. Okay, I'm back. So then if we have an even power, negative coefficient, okay, it's not necessarily going to look like a parabola. But at the end behavior, because it could be some long-all polynomial, but as long as the leading coefficient is negative and it's a degree that's even, then it's going to be down, down. Okay, or as x approaches infinity, f of x approaches negative infinity, same kind of thing there. Odd power, positive coefficient. Then it's going to have, so what you want to think is, you can think it has the same end behavior as a cubic. Like that's fine to tie it to that, just know the whole thing doesn't look like it, it's just the end behavior. So it would look like this. And then if I have an odd power negative coefficient, then it would have the same end behavior as a cubic that was reflected, so it would be up, down. So if I gave you this, okay, and then I don't expect you to be able to tell me what the equation is of that right now or anything, but you should be able to tell me, is the leading coefficient positive or negative? Positive. And would the degree be even or odd? Even, okay? You see how that works there? All right, and then if I gave you this, okay, is the power, or is the degree even or odd? Odd. And is the leading coefficient positive or negative? Negative, okay? Does that make sense? We need to kind of be able to do it both ways. All right, so flip this over. And so it says, use the leading term, give the end behavior of each polynomial. Make sure that if you're going to use the first one, that they're actually in order, all right? And these are, right, so that means that this is a fourth degree. What do we call the fourth degree? It is even, yes. But what's the name quartic, yeah. So it's quartic, and it is even, and it's negative. So since it's even, that means it's the same. It's either up, up, or down, down. But since it's negative, it is down, down. Okay? Easy enough? So look at number 2. What would you call number 2? Quintic. Good. So since it is odd, that means they're going to be opposite. And since it's negative, that means it's going to have the same end behavior as a cubic that's been reflected. So it looks like this. All right, y'all do 3 and 4. No, think about what a 7-sided polygon is called. It is not a septagon, though. Okay. No. Starts with an H. Heptic. Why is it always like H? Okay, so then since it's odd and it's positive, it's going to be down, up, like so. Okay. Everybody okay with coming up with that right now? Because that's going to be a piece of what we need in order to be able to sketch our polynomials tomorrow. All right, any questions? All right, we're going to skip. We don't need to do 5 and 6. Let's look at 7. So it says, describe both the power and the coefficient of the leading term of the polynomial. So I have no idea what the actual, equation looks like at this point, but we should know that, first of all, would this be even or odd? Odd. So we have an odd power. And would the leading coefficient be positive or negative? Negative. Okay. Questions about that one? All right, then you do number 8. What? Okay, so is this an even or odd? Even. So it has an even power, and the coefficient is what? Positive. Okay, good. Any questions on that part? We good? All right, so let's talk about our turning points. So the points at which the polynomial switches direction from increasing to decreasing, that sort of thing, that if the turning point is higher than any nearby point. So like this one right here, this is higher than all the points in its neighborhood right around it. Not necessarily of the whole thing, just right there. Then we would call that a what? Very good, a relative maximum. Okay. If the turning point is lower, like this one, than the ones in its neighborhood, then it is called a relative minimum. So as somebody stated earlier. So that means we could have an infinite amount of relative max and mins, yes, but you can only have one absolute max or absolute min. Okay. All right, so maximum and minimum values are called extrema, and extrema are a type of critical point. So your turning points define where the function is increasing or decreasing and when it changes. So these turning points are very important when we graph these, but they're also very important to what you're going to be looking at when you get into the calculus of it. So like right at the beginning, this is the type of thing that you're doing in there, and you're figuring out everything else we figured out plus where the relative max and mins are. Mathematically, by hand, it requires calculus to find them. That's why this next part down here says use the calculator to find them. That's really kind of a waste of time. Sure, we could put it in the calculator, we could push some buttons and it'll say, oh, your relative minimum is at, -2.3. Well, big whoop, you push buttons, you don't know why it is that and where it came from, right? I mean, if you're doing an application problem and you needed to know it, that's one thing. But as far as us graphing them, we're not going to use a calculator to guess at the points, okay? It's just not going to happen. So these aren't going to be something we can find yet because it takes skills you don't learn until next year at least. But I didn't take it off of there because I at least wanted to, make that known. That's why we're going to sketch polynomials and not graph them, because we're not going to know some specific things about them, but we'll be able to get the shape, we'll know some zeros, we'll know some other things that are important, and then this just gets filled in next year. Okay? We good? Any questions at all about any of this? On the assignment, there are 2 pages that come with the assignment. The blue one is only one-sided anyway. The gold one has 2 sides, but you're only doing the front. Okay?